So that's how the question was, eh? Anything that's not correct here?
That's how it was.
Yeah?
RC was 2 kilo ohms.
RC was 2 kilo ohms and RB 3 kilo ohms, eh?
Yes.
RE 3 kilo ohms.
Yes.
Interchange them. Now let's get what you're getting. Which values are you getting? Which values did you get specifically?
IE.
IE, what did you get?
I have 1.43.
1.43 milliamperes, eh?
Yes.
IC.
IC I have 1.86.
IC is 1.86. IC cannot be greater than, it can never be greater than IE.
Greater than IE.
Should be a value of like 1.4. But I'm suspecting it's 1.86. So IE is the one which could be wrong. Mercy, what do you have? Anyway, can you give us your values, all the values that you have? So you had 1.43, then 1.86.
Okay. Oh, me. Sorry. Yes, 1.86. And then my VCE.
You see?
Sorry, IB. IB is also 1.86.
IB is 1.86.
Yes.
Is it milliamperes?
And sorry.
Then we see
VCE have gotten 1.99.
1.99 volts.
Yes.
Yeah. Anybody? Amambe, you have some value?
I've not been able to go beyond the first one. Only able to calculate for IE.
What about Brian? So I can do let me do it for you. Yeah, so let's check which ones you got right. And remember, we are using those formula. So I will start from the formula of VRB2 is equals to VCC times RB2. So VCC times RB2 divided by RB1 plus RB2. So if we substitute the values, you're going to get 10 times 5 divided by 5 plus 5. And actually that gives us, it gives us 5 volts. You confirmed? That's what you have, 5 volts.
That's right.
Which is equivalent to VB. It's actually the same value as VB. And remember, we have said, at some point we said that VB is equals to VBE. VBE plus IE RE. And from here, actually, you can now be able to get the value of IE because the others are known. So if you interchange the equations, you have IE as the subject of the formula, which will basically be equivalent to VB minus VBE. Then we divide by RE. So if we substitute the actual values, we get 5. So 5 volts minus 0.7 volts then divide by your RE, and the RE is 3K, so 3 kilo ohms. So 3 times 10 to power 3. Which values are you getting for this? Those ones who have calculators, please, you should be helping us faster.
1.43 milliamps. 43 milliamps.
1.43 milliamperes. I think that's what you are getting. And you can
Chances of a
see
lifetime.
that's correct. So if you have IE, then by the you also have IC, and you also have IB. And this is what happens. IC is equals to IE so IC is equals to IC. IC is equals to IE times alpha. So alpha, I don't know how we can represent it anyway. For now, let's use that. And please note that alpha is supposed to be beta divided by, it's supposed to be beta divided by 1 plus beta. So times IE. And if you multiply, we know 100 divide by into brackets 1 plus 100. And then we multiply the value that we have, 1.43, to the power of 3. Give me the results. It's actually 100 divided by 101 times 1.43. Becomes to 1.42. 1.416 more approximate milliamperes. That's what you expected to get.
Okay.
And then IB is basically IE minus IC. Or sometimes you could take the easier one, which is IC divided by it's IC divided by 100. Of course, which is better, you know that. So if you take the actual value of IC, which is this one, and then we divide by 100, then this one gives us, because this times 10 to power 3, times 10 to power 3. That will be equivalent to 10 to power negative 3 is this one. Milliamperes is negative 3. So this comes to 1.46 times 10 to power negative 5. That will be the results. So you already have those 3 values. And this is actually amperes now.
10 power negative 3.
No, negative 5, sorry. Because it's negative 3, then if you divide by 100, this one goes up to minus 3, minus 2.
Becomes a negative. Yes. Minus 5.
That becomes minus 5. Eh? Then,
Yes.
now, since you have those values, it's very easy to get VCE. And we know VCE from the collector emitter equation. It will be VCC minus ICRC minus IERE, which will be equivalent to, we take those values that we have there of 10, then we subtract IC, which is 1.416 times our C is 2K, so 2. So because both of them, one is times 10 to the power negative 3, the other one is times 10 to the power 3, they cancel out. Then you are left with IE again will be 1.43. We multiply by RE is equivalent to 3K. So the powers cancel out and you're left with these values. So effectively what do you get? When you multiply them and subtract, so this times 1.4.
9.
Get it? What do you have?
Okay.
4.8.
1.416 times 2 plus 1.43 times 3.
2.878.
So it will be 2.878.
Yeah.
0.878 volts. Yeah, those are all the parameters that I was looking for here. Anybody who has an issue with this? Can somebody indicate this transistor is operating in which region? So according to the characteristics of the output characteristics, where we have VCE here.
I think it is in active region.
VCE, yeah, it should be in the active region, that's correct. But it's close to what? It's close to saturation or cutoff.
Breakdown. Go to the breakdown region.
Yeah. Remember we talked about those regions. So
Yeah, it's slightly above
this is 10.
active region.
This is 10. volts, and we don't have this one in saturation, but we are interested in this point, which is basically around 2.8. That's what you're interested in. And remember, saturation was here, cutoff was this side, active is here, breakdown is when you go beyond. So that's what you expected. But later, let me introduce another concept which you call the this load line, and you will see how it works out. But that's what we are supposed to do. And I hope all of us are clear with that. So please note that I will request you to go and do this one. I'll give you an exercise. Let's go and try this. So I will replace all these. But I hope you have taken the image for this to try before I upload the video online.
What's the name of your channel?
It's Omaya lecturer just Omaya lecturer. Omaya lecturer. Just bearing the name of the website.
Okay.
So please know that I want you to I would want you to go and try this. We repeat the same questions, but I'll change this to 4K. I change this to 3K. I change this to 4K. And this one remain the same. So calculate the same parameters that I asked you to calculate earlier. So you'll do that question later. But there's something I want us to talk about, which you call the DC load line. I'm not sure. It's actually appearing after talking about the single stage amplifier. But this should be the last thing usually we deal with when you're handling the amplifier. So I'll come back to it. One which you have seen there indicating the single stage amplifier. But now let's talk about the DC load line. That's one concept I think we need to understand. Also, I can introduce today, see whether you can be able to get something out of it. Please note that the DC load line is the line on which the transistor operates in. So the DC load line. So it's basically a line along which the transistor operates. And it's obtained from the collector emitter equation, which we had just handled. collector emitter equation. That's where we get that line from. And it usually appears on the output characteristics. So it appears on the output characteristics of our transistor. So I'll go down. And you'll be able to see how that line comes about. So I want you to have a look at the collector emitter equation that we are discussing about. That equation is usually given by a collector emitter equation. You guys, what is the collector emitter equation? It's given by VCC is equals to ICRC plus VCE plus IERE. That's the collector emitter equation. That's what we usually call the collector emitter equation. And I've actually talked about it several times, not just now. So can we make IC the subject of the formula? And what you do to do that, let's just repeat the same equation, and we'll have it in such a way that IE, we change it to IC. For you to change this to IC, you need to multiply, you need to divide by, so you divide by alpha. That's more alpha. Let's take it to be A. Alpha is, our A is basically alpha. So please know that if you do it this way, when this is alpha, then it gives you IE. You have replaced that with IE. So sometimes you can also approximate. If we actually say that IE, well, that's what I would want us to do. IE is almost equals to IC. We assume as an assumption, then what will happen to this equation? It becomes, this changes to IC. And if you want to make IC the subject of the formula, what you do? It will be given by VCC.
It will be VCC minus
As
VCE
VCE, or that in the brackets divide by, and the brackets RE, KRC plus RE. Please note that that's what we have for the equation of IC being the subject of the formula. But now I want us to use that. And how do you use it? We'll have VCC on its own. Divide by RE plus RC plus RE, and also VEE divided by RC plus RE. That equation is in order because we are just taking the denominator to be common to this, and it is still fine. What happens if I interchange this? In which case I'll have this appears at this point instead of the other point, the other side. If you look at that equation keenly, you realize that this IC, this VC, so our graph will be having IC versus VC, and in that case, then you have the equation of a straight line, which is given by y is equals to what? The equation of a straight line is usually mx plus
C.
plus c. So
Plus
which
C.
one? What's y? Y is equals to IC,
Is IC.
and then m is equals to negative 1 over RC negative 1 divided by RC. That's m. Then x is equals to VCE. And finally, C is equals to this value here, all of this. I hope it makes sense how we do a straight line equation here. So please note that that straight line equation given by this will have the intercepts such that the IC intercept will be given by C. That's what you usually have. As in the Y intercept. The Y intercept is given by C. So that's what you usually have.
Yes.
Yes. Yes.
And the x-axis or the x-intercept is usually given by the value where y is equals to 0. Is that also correct?
Yes. When y is 0, you get the x value.
Let's look at the diagram I'm trying to talk about. It should look like this. And then you have your x-intercept and the y-intercept. Because this will be our x, which is basically the VC. These are VC. And this is IC. So IC takes us up. And VC takes us this side. So from here, this intercept will be given by this value. We need to place it here. So it's a huge value, but we need to place it somewhere there. Please know that it's our intercept at this point. It appears at that point. Then The VC intercept is when we take IC to be 0. If you take IC to be 0, what do you get? The whole of this should be equal to the whole of this. Eh? In that case, then it means your VC is equal to VCC. You can just check on that. VC is equal to VCC. So at this point here, you're going to have it as VCC. Please know that this line is what we are calling the DC load line. This one. This value is usually called IC sat. IC saturation. So this one is called, it's basically the IC sat, as in it means saturation. Eh?
Okay.
And this one is called VC cutoff. So cutoff. That's okay?
Yes.
Those two intercepts, that's how we call them. The operating point, usually we also talk about the operating point, which is basically the Q point. We usually call it Q point. This point is given by the value you are getting for IC and VC. Please note that those values we calculated up there. With what we were doing, IC we calculated, VC we calculated. That Q point can be anywhere here. You can have it anywhere along this line. So you can have like this one and we call it our Q point. Yeah. So those are the most important concepts you discuss when you are dealing with the DC load line. The y-intercept, x-intercept, the Q point, which is the operating point, and then you get your line. So this is what I want you guys to do. So I'll give you this as an exercise you can go working on. Based on the example we did earlier. The example done earlier. Determine the DC load line. Determine and draw the DC load line. And indicate the operating point, which is the Q point. Which example am I talking about? The one we just did.
Okay.
That's okay?
That's okay.
Yeah, and then now the other one that I gave you, see, I gave you another one which you are supposed to do some values I had given.
Yes.
Also include that one.
Yes. So there are two.
There are two of them. So I want you to do those two examples by drawing the DC load line, obtain it, and then you draw it, looks like this, then indicate the operating point or the Q point for the two. Is that okay?
Okay.
Then we meet next class, the next time.
Okay.
All right.
Yes, I will post this online so that you can be able to check.
All right. Thank you.
Yes, welcome. Good night.
Good night.